All right, let's dive in. Today, we're getting into the nitty-gritty of the software that's supposed to be powering our autonomous future. For what, a decade now? We've been hearing about the coming revolution of self-driving cars, delivery bots, you name it. But let's be honest, while the hype is massive, the reality is kind of lagged behind. So we're going to peel back the layers of the code itself to figure out why and what the new game plan is to finally get this stuff working at scale. You know, to really get a handle on the problem, you just have to follow the money. It tells you everything. On one side, you've got a tech giant like Alphabet. They're pulling in about $1.5 million in revenue for every single person they employ. Now, look at the other side, a top-tier autonomous vehicle company like Aurora. And their revenue per employee is, well, basically negligible. Over 70% of their cash is just going straight into R&D. Now, this isn't just a bad quarter. It's a symptom of a really deep, fundamental issue. The autonomy industry just isn't scaling the way software is supposed to. Which brings us to the big question. So what gives? Why is this trillion-dollar industry, with some of the smartest people on the planet, kind of stuck in neutral? We've seen other tech revolutions just explode, so why not this one? Well, the answer isn't in the hardware, or the sensors, or the fancy cars. Nope. The real issue is buried deep, deep inside the software. So to find it, we're going to peel this thing back like an onion, layer by layer, starting with the big picture. Okay, layer 1. The autonomy stalemate. See, for a long time, the whole industry has been stuck on this old way of doing things, what the experts are now calling Autonomy 1.0. This is the old school approach to building self-driving software, and honestly, it's the main reason progress has hit a wall. It's a philosophy where you solve every new problem by just throwing more engineers at it, not by making the system itself smarter. And as we're about to see, that's created some serious bottlenecks. This problem really boils down to 3 big headaches. First, you've got just sheer complexity. Autonomy 1.0 systems are this tangled mess of different modules and hand-coded rules. It's so complicated that it takes a massive team of engineers just to keep the lights on. Then there's the human data bottleneck. This approach is totally dependent on huge fleets of cars driving around in the real world and then armies of people manually labeling all that data. It is painfully slow and incredibly expensive. And finally, you hit the generalization wall. Because the whole thing is built on specific, handcrafted rules, it's really brittle. If you want to move the system to a new city, you basically have to start over. It just doesn't adapt. And if you want proof, just look at the numbers. This is real-world data from AV testing in California. Between 2018 and 2022, sure, the number of miles driven went up a bit, but look at the disengagements. That's when a human safety driver has to jump in and take over. That number has been stubbornly, frustratingly high, over 2,000 times every single year. The progress is almost flat. It was clear. Throwing more money and more engineers at the problem wasn't fixing it. They needed a whole new playbook. So if the old way is broken, what's the fix? Well, that brings us to our next layer, this new paradigm called Autonomy 2.0. And the philosophy here is a complete 180. The goal isn't to just hire more engineers. The goal is to build software that actually learns, a system that gets smarter and more capable the more data and computing power you feed it, instead of needing a person to hand code a solution for every little problem. And the shift in thinking is pretty profound when you put it side by side. Autonomy 1.0, that scales with human effort. You find a bug, you hire an engineer, they write a rule to fix it. That's the loop. Autonomy 2.0 scales with data. Instead of writing rules, you flood the system with massive amounts of information, a lot of it from simulation, and you let the machine learn the solution. This is a game changer because it moves the bottleneck from how many people you can hire to how much computing power you can get your hands on. And here's what that looks like in practice. It's this really powerful new development cycle that revolves around something called a digital twin. You start with your physical cars collecting data in the real world. Then you use that data to build an incredibly realistic simulation, a digital clone of the world. And inside this virtual playground, you can test your software like crazy. You can run millions of miles, throw every weird edge case at it, all safely and cheaply. Then, once it's better, you deploy the new software back to the real cars, they collect more data, and the whole cycle just keeps repeating, getting smarter and smarter each time. Okay, so we've got a whole new philosophy. But how does that actually change the code itself? You know, the part that makes a robot decide to turn left instead of right? Well, let's peel back one more layer of the onion and look at the planning algorithm. We're getting into the real guts of the system now. The old method is called cyclic planning. Just imagine you're driving down a perfectly straight, totally empty highway. A cyclic system is like a nervous driver who's constantly recalculating the route over and over, maybe 10 times every second, even though absolutely nothing has changed. It works, sure, but it's incredibly wasteful. It just burns through processing power for no good reason. Now, the new way is event-based planning, and it's way, way smarter. Same empty highway, the system creates one good plan and just follows it. It only bothers to create a new plan when an event happens. You know, a car suddenly merges into your lane, or you start to drift, or your exit is coming up. It only thinks when it actually needs to think, and that frees up a ton of computer brainpower for other important stuff. And the difference this makes is just staggering. Real-world tests comparing these two methods found that the event-based approach cut the number of planning calculations by about 95%. Let me say that again, 95%. That's not just an improvement, that's a revolutionary leap in efficiency. It's the definition of working smarter, not harder. Okay, so the algorithms are way smarter and more efficient. That's great, but how do you build them so you know for a fact that they're safe? In a car or a plane where a failure is catastrophic, you can't just hack something together. You need proven architectural blueprints. In the software world, we call these design patterns, and this brings us to the next critical layer. And here's the key thing, you can't just use any old design pattern. They have to be specifically adapted for safety. For instance, a system needs timeout monitoring, which is basically a way to make sure it never gets frozen waiting for an answer that isn't coming. It needs designated safe states. That's your emergency fallback plan, a guaranteed safe condition if anything goes wrong. Then there's failure isolation, which is huge. It stops a tiny bug in one part of the system from bringing down the whole car. And finally, you absolutely need priority-based events, which makes sure that a hit the brakes now message always gets processed before a change the radio station message. Makes sense, right? And what's really cool about this is that engineers aren't having to reinvent the wheel. They're actually borrowing battle-tested safety blueprints from the world of avionics, airplanes. They're taking ideas that have been proven to work under the absolute strictest safety standards on Earth and are adapting them for cars. It's like giving our cars an infusion of aerospace-grade DNA. We finally made it to the very core of our software onion. All of these new ideas, these smart algorithms, these safety patterns, they all have to run on something. They run on an operating system. But it can't be just any OS, like the one on your laptop. No, this requires a special kind of foundation where timing isn't just a suggestion, it's an ironclad guarantee. To really get this, let's compare two types. Your phone or computer uses what's called a soft real-time OS. If you're streaming a movie, it tries really hard to hit its deadlines. But if it misses one by a few milliseconds, the video just glitches for a second. It's annoying for sure, but it's not a disaster. A car's safety system, on the other hand, needs a hard real-time operating system, or RTOS. Here, a deadline is absolute. Missing a deadline, like telling an airbag to deploy even a fraction of a second too late, is a complete catastrophic failure of the system. And that really is the bottom line. For all the critical functions that keep you safe, the steering, the braking, the airbags, there's just no wiggle room. You need a hard RTOS that can guarantee with mathematical certainty that the most important jobs get done exactly when they're supposed to, 100% of the time. It is the rock-solid foundation that all the other layers of safety are built on. So let's just recap that whole journey through the onion. We started with a massive business problem, the Autonomy 1.0 stalemate, where nothing was scaling. The solution to that was a whole new philosophy, Autonomy 2.0, all about data and simulation. This new paradigm makes it possible to use much smarter algorithms, like event-based planning. And those algorithms are built using super safe blueprints borrowed from industries like aerospace. And all of it, the whole shebang, runs on that critical foundation, a hard, real-time operating system that guarantees precision. See how each layer builds on the next? And that all brings us to the final big question. This new software stack, this whole Autonomy 2.0 blueprint, it really does seem to solve the core problems that held the industry back for so long. But is it enough? I mean, we can simulate billions of miles, but the real world is infinitely complex, infinitely weird. Will this new approach finally be the thing that lets this industry scale? Or will reality always be one bizarre, unexpected edge case ahead of our best simulations? Well, that is still the trillion-dollar question.